Hello, Professor Simmons here. This video is about an introduction to matrices. There's a lot more material on matrices in the Boas textbook. These are just a few basics. We will think of a matrix as a two-dimensional array of numbers, or functions, or other mathematical objects. And we will use two different kinds of notation to refer to the matrix. A matrix M will be written as the letter M with a tilde underneath it. And an individual element of matrix M will be referenced with two different indices, one for the row within the matrix and one for the column within the matrix. Multiplication of two matrices or more matrices has several important properties. It is associative, meaning that if I want to multiply these three matrices A, B, and C together, it doesn't matter whether I first multiply A and B and then multiply that product by C, or whether I multiply B and C and then multiply A. I'll get the same answer either way. Matrix multiplication is also distributive, as illustrated here. If I multiply matrix A by the sum of matrices B and C, it's the same as if I had added the product of matrices A, B, and AC. However, matrix multiplication is not commutative, generally speaking. There are special kinds of matrices for which commutation works, but those are special matrices. In general, you should not assume that matrix multiplication would commute. So in general, if I multiply matrix A by matrix B in this order, I will get a different answer than if I write the matrices in the other order before multiplying them. Let's look at how multiplying a matrix by a constant or a vector will work. And here's the notation we'll use for our matrix. So notice that the two elements on the diagonal of the matrix have the same values for the row index and the column index. So M11 and M22 are on the diagonal. The elements away from the diagonal have different row and column indices. So here M21, M12. If I want to multiply this matrix by a constant, well, all that happens is that every element of the matrix gets multiplied by that constant. So that's very straightforward. Let's go to the next slide to look at more complicated multiplication. Here, let's multiply our matrix by a vector. So I write out what I'm going to do in order to multiply. Operationally, it's as though I pick this vector V up, twist it so that the element V1 aligns with M11 and the element V2 aligns with M12. I multiply the M11 by V1 and M12 by V2 and add them together. Then I move the rotated vector down a row and multiply it by the next row of the matrix and get the answer here. If I call the answer by the name U, with a vector sign on top, notice that any component of U, so the components are like the rows of the vector, any component of U corresponds to the appropriate row of the original matrix with a sum over the column index of the vector and the matrix. Similarly, if I want to multiply matrix M by a different matrix, D, I see that I do this by treating the first column of matrix D like the vector above, and I do the multiplication of that first column of D by matrix M in the same way as above. And then I treat the second column of matrix D like another vector and perform the multiplication with matrix M and get the answer here. Multiplying a matrix by a vector gave me a vector. Multiplying a matrix by another matrix yields another matrix. And here, if I call this one N, I can see that the individual components of the new matrix N corresponds to multiplying row I of the original matrix M by a column J of the original matrix D, and that's how I get an IJ component. This kind of multiplication generalizes to an arbitrary size of square matrix, vector, constant, what have you. I've shown this for 2 by 2 just to make it fit on the page. Let's go on and look at some properties, some intrinsic properties of matrices on the next slide. There are several important attributes of a matrix that you will use over and over when you use matrices for calculations in other contexts. One of them is called the trace, and that is very simply the sum of all of the diagonal elements of the matrix. Easy to describe, easy to calculate, but very useful. A second attribute is called the determinant, which is sometimes written in this way, with vertical bars surrounding the matrix. There are a couple of different ways to represent the determinant. One is as a sum of terms where there's an element for each column of the matrix, or equivalently you can write it as a sum of terms where each row of the matrix is included. They're equivalent since they're the same number of rows and columns in a square matrix. Note that instead of using the sum symbol, as for the trace, here I'm using the epsilon symbol to combine terms, and that is because the epsilon symbol, as you learned earlier in the course, introduces a minus sign every time you swap the order of two elements. So every time you swap the order of two columns here or two rows here, you pick up a minus sign. For example, if we look at the determinant for a 2 by 2 matrix A, the first term is the product of the diagonal elements, and the second term turns out to be the product of the off-diagonal elements. And if you compare the two terms, you see that in comparing this one and this one, to get to the second one, I have permuted the second index of the elements here. That permutation is responsible for the minus sign. In looking at the determinant for a 3 by 3 matrix, we get a formula here that's probably familiar to you if you've used a 3 by 3 matrix to perform the cross product of two vectors. And again, you see that in key places, minus signs emerge whenever you are swapping the order of two different indices. Now, this way of writing the determinant generalizes to any size of matrix. I simply gave examples for 2 by 2 and 3 by 3. It's a nice way to write the determinant because it makes it clear how two different properties of the determinant come about. One property is that if you took any single row or any single column of the matrix and multiply it by some number, alpha, the new matrix would have a determinant that was the same as the old determinant except multiplied by a factor of alpha. And you can see that because in the epsilon, you would be multiplying one of these a's by alpha, but only one of them in each term would pick up a factor of alpha. Since every term in the sum picked up one factor of alpha, the whole answer would be bigger by a factor of alpha. That turns out to be useful in doing certain proofs. A second thing that is true and is extremely useful is that you can see from this form of the determinant that if any two rows or any two columns of the original matrix were the same as one another, then because of the epsilon, that would mean the matrix had determinant 0. Because if two columns were the same, then when you permuted them, the epsilon would tell you the answer should be off by a minus sign. But if the two columns were identical, the answer couldn't have changed at all, and that contradiction could only be resolved by having the determinant be 0. In fact, remembering the first property above, we realize this second observation also applies if two rows are not quite identical, but one is proportional to the other. Because if one is proportional to the other, we could pull out that constant of proportionality and outside of the determinant altogether, and then be left with a situation where two rows or two columns were identical, and then the determinant would vanish. So, important properties of the determinant. Why the determinant is so important, we'll see in a minute. Finally, a matrix has an inverse. Just as the number 5, when multiplied by the fraction 1/5, gives 1, so every number has an inverse, every matrix has an inverse. If this is our matrix M, there is some other matrix, M inverse, such that when you multiply them together in this order, or even in the opposite order, as it happens, the result is called the identity matrix, meaning the diagonal elements are each equal to 1, the off-diagonal elements are each equal to 0. Generally speaking, if you have two different matrices and you take the inverse of their product, that is equal to the reverse order product of their inverses, as written here, and that turns out to be useful in various contexts. It's also fairly easy to prove. Here, let's assume it's true. I write AB times its inverse ought to equal 1, and let's assume that this the inverse of the product is in fact the reverse order product of the inverses. In that case, the BB inverse cancel out and become an identity matrix, so we're left with just AA inverse, which again combine to give the identity matrix. So you might wonder, how do you find the inverse of a matrix? Well, for a 2x2 matrix, it's straightforward. The inverse of a 2x2 matrix is 1 over the determinant of that matrix times a 2x2 matrix that changes the sign of the off-diagonal elements. And, there is a typo there. They should both have, both of them should pick up a minus sign. I will correct that in a future video. And the two diagonal elements have exchanged places. We can check that by multiplying this form of the inverse matrix by our original matrix, and if you go through the algebra carefully, you can convince yourself that the off-diagonal elements are 0, and the diagonal elements cancel against this factor here, so we end up with the identity matrix. Now, more generally, as described in the Boas textbook, there is a formula for the inverse of a larger matrix, and the only thing I want to point out here is that that formula for the inverse of a larger matrix still includes a factor of 1 over the determinant of the original matrix. So no matter what size our square matrix is, in order for it to have an inverse, the matrix may not have determinant 0. If a matrix has determinant 0, it is called a singular matrix, and no inverse exists. And again, we'll find this is important. Well, we will use all of these properties and ideas in class to explore particular classes of matrices and then apply them to physics.